Hello guys, welcome to the channel. So our complete machine learning tutorial is finished. Now our next topic is deep learning, right? So let's start with deep learning. So in today's video, we will discuss deep learning introduction. Okay. So what is deep learning? Think about it. So deep learning is a subset of machine learning. Okay, subset of machine learning. Machine learning is a subset of AI, and deep learning is a subset of machine learning, which uses artificial neural networks. Remember that artificial neural networks, ANNs, with multiple layers to learn pattern from the data. Now, think about this. Like think of it like this. Now, as per traditional programming, what you do, you have you must have inputs, then you set some rules, means you coded some rules, and then you got the output. In machine learning, what we saw, we had input, output, we trained the model, it learned the rules and it predicted the value, and we got the output, right? Now deep learning, in deep learning we will have huge amount of data. Okay, huge of amount of data. Plus, it will have neural networks. It Because of neural networks, it will learn complex patterns automatically. Okay, it will learn complex patterns automatically. So, deep learning, you must have heard about it. Deep learning is inspired by the way the human brain works. Let's discuss what it means. So, our human brain our humans brains neuron, this is okay, human brain neurons. Okay, our human brain estimated contains 86 billion neurons, right? You can search about it on Google. Our brain contains estimated 86 billion neurons. Okay, so this is a human brain neuron. Okay, now let's divide this part by part. First is your dendrites. Okay. What dendrites do? It receive information from other neurons. Okay. Suppose your eyes see a car. So this signal will reach neurons through dendrites. Okay. Now, second part is your cell body. Cell body. The center part of the neuron. This one, the center part of the neuron. What it will do? It processes the received information and decide what to do next. It will decide what to do next. Okay. Now third thing, axon. This is axon basically carries the signal from the cell body to other neurons. Okay. It is like a communication wire. Communication wire. This okay. Now fourth part is your synapse. What synapse do? So it has the information, right, through axon, synapse. Now it will it will pass the information to the next neuron. It is like a connection point. After this, you will have another neuron. It is like a connection point, right? That is what synapse. So this is how human brain's neuron works part by part, from dendrites to cell body to axon, axon to synapse. This is how a neuron works. And there are multiple neurons in our human brain. Okay. Now, this is our, in deep learning, this is our artificial neuron. Artificial neuron. Okay. So scientists copied this human brain idea and created their own artificial neuron. Okay, so your dendrites became your inputs, your cell body became your weighted sum plus bias. I will explain. Axon became activation function. Okay, this is your weighted sum plus bias. I will explain that. Axon became your activation function and synapse became your output. Okay. Now, Let's understand. This is I1, I2, I3, I4. These are your inputs. These are your inputs. Suppose we are predicting a house price. Okay. Now might be I can have I1 as area, I1 2 as bedrooms, I1 3 as the how old your home is, and I4 your location score. I might have these features. Okay, these are my inputs. That is your dendrites. Now step two will be your the artificial neurons will basically take inputs and perform some calculations. Okay, each input have some weights. Each input some have some weights plus bias. Now, what is weight and bias? Weight is nothing but it tells you the importance of that input for our model. Means that input, suppose I1, what is the importance of how much important is my I1 for my model? That is what our weight. Okay. Now, bias is nothing. It is an extra value added to the weighted sum. This is what weighted plus bias. That is your step two. Okay. That is your cell body. Okay. Now, which means weighted sum plus bias. It will take inputs and will perform some calculations. Okay. Now, third part, activation function. Now, activation function here, neurons decides, should I pass the signal forward? Should I pass the signal to forward or not? Here, neurons decide in activation function. Now, basically, activation functions introduces non-linearity. Okay, because of activation function, deep learning models learn complex patterns because of activation function. Deep learning models learn complex patterns. Okay. Now, fourth part is your output. So this is the comparison, like how scientists copied the idea of human brain for deep learning for our artificial neural networks. Okay. So that's how it works. Although we will basically cover all the thing practically and theoretically both, like how we covered machine learning, all topics practically and theoretically. Okay. Now, why do we use deep learning when we have already machine learning? So your traditional machine learning struggles with these kind of data, images, videos, speech, natural language, complex patterns. So our traditional machine learning struggles with these things, with this kind of data. Okay. So deep learning can automatically find important features from your raw data, right? This is your raw data. This is not your tabular form data, like your Excel sheet or your SQL data. Okay. So let's understand this by an example. Suppose for cat versus dog classification, what machine learning will notice? I will have a data and it will notice ear shape, tail length, fur color. On the basis of these inputs, it will decide this is a cat or dog. But in the case of deep learning, I will provide images and it will learn all the features automatically from images, right? This is what deep learning is. This is what the importance of deep learning. Okay. What is neural network? Uh, Basically, it is like a human brain consists of interconnected neurons. Okay, like our human brain contains multiple neurons, estimated 86 billion neurons, right? So that is what your neural network. It contains interconnected neurons. A structure is input to hidden layers, and then from hidden layers to output layer. Okay, this is the structure of your artificial neural. Now, Each neuron will receive input. Each neuron will receive input like a human brain. I have already explained. Perform some calculations and then process passes output to the next layer. Okay, next neuron. Okay. Now, these are some types of deep learning. ANN, artificial neural network. It is used for tabular data, basic prediction tasks like the machine learning thing. Tabular data like your Excel sheet, SQL data. We will use ANN for that. Second is your CNN, convolutional neural network. It is used for image processing, computer vision. You must have heard about these things if you are learning machine learning, deep learning. Okay. Now, CNN for images and computer vision. All thing we will discuss. Okay. Slowly. Okay. Third thing is your RNN, recurrent neural network. It is used for sequential data, time series, text. Okay, how my LLM models, how it predicts the second word on the previous word. Like the sky is blue. Your is blue depends on your sky, right? So this is how RNN works. This is This is on what RNN works. LSTM. LSTM is nothing but your advanced version of RNN. Okay, handles long-term dependencies. Okay. Now, fourth thing is your transformer. It is most powerful architecture today. Okay, it is used in ChatGPT, Gemini, Cloud, DeepSeek. We will discuss all these things. Okay, one by one. Like we have covered all topics in machine learning both theoretically and practically. We will discuss all these things. So these are the types, and we learned what is deep learning introduction. This is what all about deep learning. Okay. From the next video, we will discuss first topic is our single layer, uh, sorry, single layer perceptron. That is our next topic we will discuss. Okay. Thank you. Hello guys, welcome to the channel. So our today's topic is single layer perceptron. Okay. Now what is single layer perceptron? A single layer perceptron is the simplest neural network model used for binary classification problems. Remember that binary classification problems for linear data. For linear data, okay? It is used single layer perceptron. It is the simplest neural network, okay? So it takes multiple inputs, multiplies them by weights, and adds a bias and applies an activation function and then produces an output. Okay. For example, suppose a bank wants to decide whether to approve a loan or not. Okay. So your inputs are suppose income is 80,000, credit score is 750, and existing loan is no. These are your features, means columns. Okay. Now the perceptron processes these values and outputs one for loan approved and zero for loan rejected. Okay. Now these are components of single layer perceptron. Let's see one by one. First is your input layer. Input, that is X. Suppose you have these inputs. These are features of the dataset. Age is 25, salary is 50,000, and experience is 2 years. Okay. These are three features. Suppose X1, X2, and X3. There is no fourth feature. Okay. So these are my three features. First, input. Now, second is your weight. What is weight? Each input has a weight. Each input. Weights, weights tell the importance of each feature. Okay. Suppose your salary has weight 0.8, age has weight 0.2, experience has weight 0.5. So look at here. Income has the highest weight. What it means? Income is the most important feature for us. That is what weight describes us. Okay. Now third one is bias. Bias basically shifts the decision boundary. Think of it as a threshold adjustment. Without bias, decision always starts from zero, and with bias, decision can move left or right. Okay. Basically, it makes the model flexible. Okay, we will understand this what we do by bias. Okay, but first understand weighted sum. Okay, so look at here. Weighted sum is your z. Now w1 into x1 means x1 is your input and weight of the weight of the x1 input w1 plus w2 into x2. Similarly, x2 is your input and weight of the that particular input w2. Similarly, w3 into x3 plus bias plus b. This is called linear combination plus b. What is bias is doing here? It is making my model flexible. How it is making my model flexible? Suppose I am calculating marks of some students. Okay, we are getting some marks of students. We have set a criteria that if a student will get 45 marks, then 40 marks, then he will be passed. He will be passed in the exam, or he will be failed in the exam, or if he didn't get the 40 marks. Okay. Now let's understand. We got a value 40 for W1 and 1 for weight is your 1 for your input, and your input is suppose 40. Now 40 into 1 plus is equal to 40, let's take 45. Our input has 45 value. 45 into 1, our weight is 1. So what is the value came? 45. Now it means the student got passed in the exam. But let's suppose we give plus b, mean bias. Let's suppose we give minus 10 as bias. So what it will do? It will basically it will decrease the value 45 to 35. Now if a student that particular student got failed in the exam because he is getting 35. So that is the basic understanding I tried to give you by this example of bias. Okay. So basically, this is how bias works. It gives a flexibility to the model. Okay. Nothing else. Now, this is your weighted sum, Z. Okay. Now fifth one is your activation function. The activation function converts the weighted sum into the final output. Final output. Okay. Usually single layer perceptron uses the step function. Okay. If z suppose if z is equal to if z is greater than or equal to 0, then output will be 1, or else output will be 0. That is what activation function is doing. Okay. So this is some mathematical representation. Suppose I have inputs x1, x2, and x3, and w is your weight is your w1, w2, and w3. Bias is equal to b. Then how we calculate the weighted sum? Weighted sum is equal to weight of the first input and into the first input plus weight of the second input and the second input plus third weight into third input plus bias. Okay, so it became z is equal to w into x. You can say plus b. This is your w into x is your dot product. Okay, now let's see. Let's understand how we can perform single layer perceptron practically. Okay, now I have this data set. I don't know this data set is linear or not. Okay, but we will try. We will just see how we can perform single layer perceptron on this data set. Okay, so let's understand this practically. Now I will import some required libraries. I will import pandas as pd, import matplotlib.pyplot as plt, import cborn as SNS. Now, last thing I will import mlextend. Okay, from mlextend dot plotting import plot decision reason. Okay. Now let's import our data. pd.read/csv. I will copy this copy path. I will paste it here. I will check my data is loaded or not by checking its first three rows. Yeah, my data gets loaded and there its first three rows. Now let's check by plotting a graph how my data is looking, whether it is linear or not. Basically, single layer perceptron is usually used on linear data set and for binary classification. One consider one condition is getting satisfied that it is a problem of binary classification. But let's see this is a linear data or not by plotting a graph. Scatter plot x is equal to age, y is equal to, sorry, age x is equal. Now data is equal to data. I will give u. I will give as placement. Okay. I will give plt dot show. Okay. So yeah, this is how data is looking like. It is not like a linear data. Okay. But let's perform single layer perceptron on this data set only. Let's see how we it is performing on this data set. Okay. Now, by the way, it will not perform good on this kind of data set, but we will check. Okay. -1 and y I will take as data. Listen. Okay. Now I will split my data set into train test training 80% for the training and 20% for the testing. Okay. Dot model selection import train test split. Now let's take all the variables x test, y train, and y test is equal to, I will call my train test split. I will take my x and y variables. I will give test size as 0.2. I want 20% for my training testing data and 80% for the training data. Now I will give random state is equal to 42. Okay. Now, now I will import Perceptron from sklearn dot linear model import Perceptron. Okay. Now let's create an object to call Perceptron. Okay. Now Let's check its parameters. Okay, alpha it is giving. Alpha is nothing but your regularization strength. Its purpose is to basically prevent the model from learning extremely large weights. Suppose you are getting 2,000, 5,000, like this kind of weights. So it basically reduces that large weights. Okay, it prevents the model from learning extremely large weights. Okay, this is what alpha will do. Suppose I will take alpha and suppose I will customize some values. Suppose I will give 0.001. Okay, now let's say this is your fit intercept is equal to true means your bias. Okay, it is true. It is by default. It is true. Then we are saying that add bias. Okay, if it is true. If I will basically I will set this as false. Then it means I'm saying that don't don't take the bias. Don't add the bias. Okay, to the weighted sum. Okay, that's what it is. Okay, now let's give only this. Now I will fit pr.fit X train, comma Y train. It gets fitted. Now let's see the accuracy of the model for both training and testing. Okay, I will give, I will replace this by test. Okay, so as you can see, we are not getting a good accuracy because this is not a linear data set. Okay, this is a kind of random data set I have taken. This is not a linear data set. That's why I am getting very low accuracy, 65 only. Okay, so so this is how we use perceptron, but usually we use single layer perceptron for linear data set. This is not our linear data set, so that's why we are getting low accuracy. And for binary classification, it was a type of binary classification, but it was not a linear data set. That is why we got an we got a low accuracy. Okay, so you can check uh, on your own data set if you have any linear data set for binary classification. Remember that for binary classification, if you have that kind of data set, then you can try this single layer perceptron on that. Okay, so that is how single layer perceptron works, and I have covered its theory and mathematical representation also, how single layer perceptron works by mathematically and practically also. Okay, so that's all in this video. And basically to counter this problem, we use multi-layer perceptron. Okay, so in the next video, we will discuss multi-layer perceptron, which is your ANN. In our next video, we will cover that. Okay, so that's all. Thank you. Hello guys, welcome to the channel. In our previous video, we have discussed single layer perceptron, and in this video, we will discuss multi-layer perceptron and some important topics related to deep learning neural networks. Okay, so first understand what is multi-layer perceptron. A multi-layer perceptron is simply multiple perceptrons connected together. Okay, see, a single perceptron can solve only simple problems like AND or means binary classification problems. It can solve. It can be solved by single perceptron. But when we connect many perceptrons in multiple layers, the network becomes much more powerful, obviously. So in that case, we will able to learn complex patterns also by our model. Okay. So simple definition is A multi-layer perceptron is a feed-forward neural network that consists of an input layer, one or more hidden layers, and an output layer. See, this is the diagram. Here it is your input layer. Suppose there are three features in your data, means three columns in you as an input in your data, x1 and x2. And this is your xn. Basically, you can have multiple input layers and you can have multiple hidden layers also. You can have n number of hidden layers also. And on the basis of input layer, basically we will have output layer also. Okay. So we can have two output layers, three output layers. It depends on like how many features I have. Like I have cat, dog, cow. Then it means I have three features. That will be three will be your output layer. Total three number of output layers will be there. Okay. So now input layer receives the input features. Input features here. Input layer will receive. For example, age, salary, experience, these are your input features, means input columns. Okay. It will fetch. Then there will be three input neurons because there are three features here. The input layer does not perform calculations, obviously. Its job is to simply to pass data forward to the hidden layer. Okay. Now, second one is your hidden layer. This is where the actual learning happens. This is where the your calculation happens. Okay. Each neuron will receive inputs. Each neuron multiplies them by weights. These things I've already discussed. Multiplies them by weights, adds a bias, and then applies an activation function. Okay. Then sends the output to the next layer. These all are done. These one thing are done on a single layer. Then it will be completed. Then similarly, then it will forward these things to the next layer. Okay. So there can be one hidden layer, two hidden layers, any like n number of hidden layers can we can have. Okay. Now, basically more hidden layers generally allow learning more complex patterns. Okay, obviously. And third one is your last one is your output layer. Produces the final prediction. Like for multi-class classification, cat, dog, horse. Output neurons will be three because we have three categories. Okay. So now let's go into the deep. How does one neural work? Remember this one neuron work. We can have multiple neurons on the basis of our features and categories. Okay. Each neuron performs four simple steps. Understand these four steps. Okay. First one, take inputs x1, x2, x3. Okay. Input is provided. Next, step two, multiplies by weights. Every input feature will have a weight. Okay. Every input feature will have a weight. Suppose x1 has a weight of 0.8, x2 has a weight of 0.5, x3 has a weight of 0.2. So because x1 has 0.8 weight, it means this feature is the most important feature for us. Okay. So similarly, same thing I have written here in my notes. Weights represent the importance of each input. Okay. Now third thing. Now add all these things. Okay, x1 into w1, input one into weight of the input one, input two into the weight of the input two. We will add all these things and plus we will add a bias. I've already discussed this thing. Bias, activation function, all these things I have discussed in my previous video. Okay. Now step four, apply an activation function. Okay. Then this output becomes your input for the next layer. Remember this. These things are done for a single neural, basically single layer. Then it same thing will be provided to the next layer. Okay. Here you can see we can have multiple layer. It will be provided same thing to the next layer. Okay. Now, now Second most important topic is forward propagation and backward propagation. Forward propagation is the process of moving information from the input layer to the output layer to make a prediction. Okay, from input layer to hidden layer and hidden layer to output layer, which gives us prediction. Okay, that is what forward propagation. Okay, and second thing is backward propagation. It it basically moves opposite. Suppose I got an error. Error moves from output. Then it will be moved to hidden layer and it will be moved to input layer to update the weights, to update the error in weights. Okay. Output to hidden layer and hidden layer to input layer. Just opposite of this. Okay. Okay. Now, second thing, activation functions. I've already discussed. So, activation functions I've already discussed. I will explain you again. What is an activation function? An activation function is a mathematical function that decides whether a neuron should be activated, pass information forward or not. Okay. Activated means pass information forward or not. This is decided by activation function. Okay. After calculating the weighted sum. This is what we were calculating here. Z is equal to this. Okay. After calculating this, the neuron applies an activation function to this. Okay. Now, where your Z is equal to weighted sum, MC is equal to all these things, activation function, and A is your output of the neuron. Okay. So basically, activation functions introduce non-linearity, allowing the network to learn complex relations. Because if we don't apply activation function, it will perform like it will only work for linear data. Okay, linear things. But when we apply activation functions, it becomes flexible and we can basically train our model to learn complex relationships, not only linear relationships. Okay. Now there are two main important activation. First one is your sigmoid activation function. So sigmoid function converts any input value into a value between 0 and 1. It is used for, obviously you can see here, it is converting any value to 0 and 1. It will be used for like binary classification problems. Okay. These are this is its mathematical representation. Okay. So its range is between 0 and 1, right? So it will be used for binary classification. That is what sigmoid activation function is. Okay. It will convert any input value into a value between 0 and 1. Okay. Now, second one is your ReLU activation function. ReLU activation function. Okay. ReLU outputs the input directly if it is possible, positive. Otherwise, it outputs 0. Okay. What it means? For example, what is its rule? Basically, this is its mathematical representation. Now, its rule is if x is greater than 0, then output will be same. What is your x? Suppose I have x has is 5, then it will be 5. But if x is less than or equal to 0, means suppose I have minus 3, then output will become 0. It's basically range is ReLU functions range is 0 to max. 0 to max. Okay. This is ReLU functions, activation functions range. And this is 0 to 1 range is for sigmoid activation function. Okay. Now, next important topic is loss function. Basically loss function is used to calculate error. Basically, suppose I have predicted the value is 0.80 and our actual answer is 1. So this is some error, right? So loss function measures this error. Okay. Basically it tells us how wrong is the prediction. Okay. Its examples are mean squared error. I have already discussed this. I have already explained by doing practically also. Second is this is used for regression problem, and binary cross entropy is used for binary classifications. Okay. Now, optimizers. An optimizer is an algorithm that updates neural network weights using gradients computed during back propagation to minimize the loss function. Minimize the loss function means the error. Error. It is used to minimize the error. Okay. So it basically updates the weights. Weights. Every input, remember I've already explained, every input will have some weights. It updates the weights using gradients. Okay. Okay. So these are its some types. Batch gradient descent, stochastic gradient descent, mini batch gradient descent, momentum optimizer. Okay. These are some of its types. Most important optimizer is your ADAM, adaptive moment estimation, because it combines the advantage of RM spot. Okay, this one, root mean square propagation, to achieve faster and more stable training. Okay, that's why it is the most important of optimizer. Okay, now last topic is your learning rate. It basically controls how much the weights are updated during each optimization step. Okay. Suppose this is called eta. Suppose eta is equal to 0.01. This means small steps. Okay, small step. If eta is equal to 1, then it means it is a huge step. Okay. So I have given you an overview of these parameters. Okay, these topics I have given an overview of these topics. From next video, in the next video, we will basically see how we can use ANN algorithm, ANN neural network for basically how we can basically use ANN practically by doing a project. Okay. So let's see how we can do it in the next video. We will basically do a project to understand ANN algorithm. Okay, so that's all in this video. Thank you. Hello guys, welcome to the channel. So our theoretical part of multi-layer perceptron is finished, and in today's video we will do a project using ANN. Okay, so we will do customer churn prediction project using ANN. So this is our data set. This data set I will give you. This data, what this data set is saying, basically this project is about bank customer churn prediction. Okay, so these are our A to H. These are our input columns, and this is our output column. So here bank customers credit scores data, age, tenure, balance, number of products, has CR card or not, means has credit card or not, is he active member or not, and his or her estimated salary. Okay, and this is your output column that customer will leave the bank or not leave the bank. One means leave the bank, zero means he will not leave the bank. Okay, so this is our data set on which we are going to build our model using ANN. Okay, I will give you this data set. Please try at your end by doing a project. Okay, so how we can do it now? First, I will import some required libraries. Import numpy as np, import pandas as field. Okay. Now I will load my data set. Suppose I will give data read slash csv, and this is my data set customer tool. I will right click copy path. I will paste it here. Now I will check my data is loaded or not by checking its first three rows. Yeah, my data gets loaded. And these are my first three rows. Okay. First, I will check is there any null value in my data set or not. No, there is no null value in it. Okay. So this data set is quite fine. But look at the data set. Do you think this data set needs standardization? Right. This dataset needs feature stream, and we will perform standardization for our input columns. Output column is perfect. We will do standardization for our input columns because I have already explained where I was covering standardization and feature scaling and why do we need to basically standardize our data. Look at these values. These are 1 1 0 0 and these are some higher values. So model will basically give more importance to this estimated salary, this balance, this kind of data. It will give more importance, but our all inputs are important. So we will standardize all my inputs. Okay. First, I will divide my data set into input and output. I will take all input columns into my X. I will give all rows, all columns, but don't give me the last column, which is my output column. And I will take my output column into my Y, right? I will take this in my Y. Yeah. So now I will perform a standardization for our X, which has our input features. Okay. From sklearn dot dot pre-processing pre-processing import standard scalar standard standard scalar. Now let's create an object to call your give a name SS. My object to call standard scalar. I will call my standard scalar. Yeah. Now I will fit transform. I already explained how standardization works in detail. You can check my video. Okay. Fit transform X. What I need to transform? My X, which is my input features. I will standardize. Okay. So it got standardized. It basically scaled our input features. Okay. Now I will convert this into a data frame. Data frame. I will take this. Okay. And columns I will give X dot columns. Okay. If you see your X, it will look like this. So can you see the difference? This value in these values and these values. You can identify the difference between those values. It scaled our input features. Okay, standardization. Now, now I will split my data set into 80% for the training and 20% for the testing. sklearn dot model selection import import train test split train test split. Now I will take all variables xtrain, xtest, ytrain, and ytest is equal to, I will call my train test split for which variables I am splitting x and y, which has my input and output features. I will give test size as zero point 0.2 as I want 20% for my testing and 80% for my training data. So I have given test size as zero point 0.2 and random state I will give 42. Okay. Now, if I will check my X train shape, so I have 8,000 records and 8 features, means 8 columns. Okay. Now I will import TensorFlow. Okay. If you don't have TensorFlow or and Keras, you can download it. Just search here, download TensorFlow. Okay. And you can go on this link and just copy this command and paste it into your CMD and press enter. It will be downloaded. Same for Keras also. Same for Keras also. Okay. In my system, it is already downloaded, so I'm not downloading it. Yeah. Again, go for it. Just copy this command and paste it into your CMD and press enter. It will be downloaded in your system. Okay. So in my system, it is already downloaded. So I'm not downloading it. I'm importing it here. Import TensorFlow. Okay. It generally takes some time to load. So from Keras, from Keras.layers, I will import dense. I will import dense. And one more thing I need from Keras dot models import sequential. Sequential. Okay. These things I need. Suppose I will check my X shape. Sorry, I've already checked. I have X train shape is 8,000 records, 8,000 rows and 8 features, right? So I will make an object to call my sequential. Okay, I have created an object called ANN to call my sequential. Okay, now, now what I will do, I will create, I will create these return patterns, these hidden patterns. Suppose I will create three hidden patterns and one output layer. Basically, I will create three hidden layers and one output layer. Okay, so I let's see how we can do it. We will create three hidden layers and one output layer. How we can do it? I will give ann dot add. I will call my dense. I will give suppose 6. This 6 means here I'm saying that this 6 means I'm saying that create a fully connected layer with 6 neurons. Okay. This is what I'm saying by writing 6 here. Okay. And I will give input input dimension as how many features you have? 8. So I will give 8. Okay. Input dimension I will give 8 and I will give activation function. Okay. So I have already discussed in my previous lecture What is activation? Okay, and what are the different kinds of activation function? We have already discussed. An activation function is a mathematical function that decides whether a neuron should be activated, pass information forward or not. This is what activation function do. So there are two types: sigmoid function. Its range is 0 and 1. ReLU's range is 0 to max. So I will take ReLU because what we are creating a hidden layer, and our hidden layer has 0 to max range. Okay, look at this, 0 to max. But in my output layer, only there is 0 to 1, right? Range is 0 to 1. So for my output layer, I will take sigmoid. I will take sigmoid. I will take sigmoid for my output layer, and for all features, and for hidden layers, I will take ReLU. Okay, so I will give activation. Sorry, I will give ReLU. Okay, now I will paste it three times here. I'm creating three layers, so I will paste it three times, and I will make a pyramid shape. Like, I will give this time 4, means it will contain 4 neurons, and you don't need to give input dimension again. So I will remove this again here. I will remove the input dimension. First time already, only you need to give input dimension. Okay. And suppose here I will give 2. This will contain 2 neurons. Okay. So, and yeah, 6 neurons, 4 neurons, 2 neurons, and activation is ReLU. These are my hidden layers. Okay. Sorry. Uh, these are my hidden layers. And now I'm creating my output layer. Yeah. I have created 3 hidden layers. Now I will create one output layer. I will create one output layer. ANN dot add. I will basically paste it here. So I will remove input dimension, and here I will give 1. It will it will contain one neuron because the output you will get into a form of 0 or 1, right? Only one output you will get. So I have given one neuron, and activation I will choose sigmoid because sigmoid's range is 0 to 1. So this is perfect for my output because although you will get the prediction into 0 or 1, the customer will leave the bank or not leave the bank. One output. Okay, sigmoid. So we have created 3 hidden layers and one output layers. Okay, same uh, same thing I have created. Okay, now this is the warning. You can ignore this warning. Now I will compile compile. I will take optimizer. If you will click the plus tab here. Yeah, optimizer. Its default optimizer is this. We have already studied in our previous video what are the different types of optimizers and what is optimizer. You can see. Yeah. An optimizer is an algorithm that updates neural network weights using gradients computed during backpropagation to minimize the loss function. Loss function is for basically calculating your error. Okay. So I have already discussed Adam is the most used optimizer. We generally use Adam as our optimizer. So use I will use Adam as my optimizer. Adam. Okay. Now, next thing, loss. loss function. I have already discussed in my previous video what is loss function. Loss function, it is basically measures the error. Okay, measures the error. Predicted 0 is 0. Actual answer was 1. So this is some error. This is calculated by loss function. And for regression problem, we use mean squared error and binary cross entropy for classification problem. So this is our classification problem, right? This is our classification problem, binary classification problem. So we will use we will use binary cross entropy as my loss function. Loss I will give binary cross entropy, right? And matrix I will give accuracy. Accuracy. Now, now I will fit my data. Right. ANN dot fit. What I will fit? X train and Y train first. I will fit this. Now, there are some hyperparameters we can do. Epochs, batch size. Okay. So I will only take these two now. Okay. There are many hyperparameters. So batch size, I will here it is its default is none. I will change this none to 100. So batch size 100. What I'm saying batch size is equal to 100 by. So I'm saying 100 numbers of records will be processed at a single time. What I'm saying here by batch size is equal to 100. 100 number of records will be processed at a single time. Okay. And next thing I will take epochs. Here it is 1. Here it is 1. So I will replace this by 50. So what I'm saying by giving epochs is equal to 50 means I'm saying that repeat the learning process 50 times, repeat the learning process 50 times over the entire data set. Okay, so that model can gradually reduce errors and learn the patterns in the data. That is what I'm saying by giving epochs equal to 50. Now let's train our model. It will take some time. Yeah, it has started training our model. So it gets trained. Okay. My model gets trained. Now let's check the accuracy first. Okay. Now, first I will give prediction. Prediction. Let's create a variable prediction. ANN dot predict x test. Okay. So if we will give this, yeah, this is your prediction. Now let's check accuracy. First, I will create a list. Prediction data is equal to list, a list, and I will give a for loop for I in PRD. This PRD, which is your ANN.predict X test. So what you will get the values 0 to 1, right? 0 to 1. 0 to 1. So how will you calculate this? 0 to 5 will be a one category, and 5 to 0 to 0.5 will be your one category, and 0.5 to 1 will be your second category, right? So this is what I'm saying for I in prediction PRD. If I 0 is greater than 0.5, then append my predict data by 1. Append my, if any, if like this 0.588, so it will convert this value to 1, and it will append my predicted data by 1. Okay, this is what I'm saying here. Okay, now else if value will be less than 0.5, PRD data dot append by 0. Okay, that's what I'm saying. So this is for our testing data. Now let's check for training data also, to check my data gets overfitted or not. Let's take this one, and first I will create a new variable predict one, PRD one, and this time I will predict on training dataset X train, and PRD1, if I in PRD1 I will say PRD1 is, then PRD data 1 append by 1 and 0. Okay, same thing I am doing here, but for training data. Here I did for testing data, and here I am doing for training data. Okay, now let's check the accuracy. For checking the accuracy, I have to import accuracy score. So I will import sklearn dot metrics import accuracy score. Okay, now first I will check for my training y train comma, for my training PRD data 1. This is I have created for training PRD data 1. So into 100. Here you can see I got an accuracy of 85.65. Now same thing I will check for testing. This time I will give y test comma PRD data. Okay. Now here you can see 85.5, little less than this, but this is not a case of overfitting. Little bit like 0.15 changes, 0.15 difference of accuracy in this. So I got an accuracy of 85%, 85.5%. Okay. Now let's predict a value. Suppose I will check my X test. Okay. Suppose I want to predict this on these values. Okay, on these values. Now, so I will give X is equal to np dot array. Okay. Now I will give my first row. I have given all the values of first rows. I will give commas here. Now, suppose I will create PRD data 2 is equal to ANN dot predict X. Okay, and I will create a new list. PRD2 is equal to my list. Now, I will again give a for loop for I in PRD2 if I is 0 greater than 0.5, then append my list PRD data 2 dot append by 1, and or else, sorry, PRD data 2, and here I will give PRD2 PRD data 2 dot append by 0. Okay, now if you will check here so append it's not okay. So there is some spelling thing. Yeah. Okay. PRD2 dot append. Now I will check my PRD2. So it predicted 0 on this data set, on this data point. So my first data point has prediction of 0. It means customer will not leave the bank. So I will check if this prediction is correct or not. If I will check my Y test, here you can see 6252 row, 6252 row number. This value I have taken, and my model predicted 0. And here you can see what was my actual value. It was also 0, right? So it means my model is performing well. We have built our model correctly. It is predicting right values. Okay. So this is how ANN works. So we have successfully built a model using ANN algorithm. So that's all in this video. In the next video, we will see how we can improve our model. How we can improve our model. Okay. So that's all in this video. Thank you. Hello guys, welcome to the channel. So in our previous video, we have built a model of customer churn prediction using ANN algorithm. And in today's video, we will discuss what are the different ways to improve our model performance. Okay. So first one is your cross validation. Cross validation topic I have already discussed in detail when I was covering machine learning. You can check that video. Okay. So cross validation is a technique used to evaluate a model on different subsets of data instead of relying on a single train test split. What it means? It means it will not simply evaluate the model on single train test split. What it will do? It will it will create some subsets of your actual data. It will create subsets of your data, and it will evaluate the model on all those subsets of data. Okay. So that is how cross validation works. Second is your train with more data. Simple deep learning model generally perform better when trained on larger data set. You can train your models on by adding your more data points. Okay, that is what this point is saying. Third one is your remove unnecessary features. Not all features contribute to prediction. You have some features, or you can say columns, which is not affecting your output that much. Means it is not that much important for your prediction or your model. So you can simply drop those features. Okay. Early stopping. Early stopping is a technique that stops training when validation performs stops improving. What it means? Means what early stopping will do, it will stop training the model when it will assume that this model will get overfitted. Okay. When it will realize that now the model will get overfitted, it will stop training the model. Okay. That is what early stopping do. Okay. Fifth one is your regularization. Regularization reduces model complexity and prevents overfitting. I have already discussed L1, L2 regularization based on last algorithms when we were discussing machine learning. Okay. So it works by adding a penalty term to the loss function. This has two types. L1 regularization adds the absolute value of weights as a penalty. Means suppose your feature has a weight of 0.5. Okay, your input has a feature of 0.5. So it will add 0.5 to the loss function. L2 regularization. If you will use L2 regularization, it will add squared weights as a penalty. Means if I have a 0.5 weight in our input, it will square 0.5 and then it will add to the loss function. This is how regularization works. Sixth is your ensemble learning. This topic I have discussed in detail when I was covering machine learning. So ensemble learning combines predictions from multiple models to improve performance. Okay, simple. Last one is your hyperparameter tuning. This already I have discussed again when I was covering machine learning. So this what hyperparameter tuning does, what we do in hyperparameter tuning. Basically, hyperparameters are settings that are defined before training begins. Means you just customize your hyperparameters values according to your need, according to your data. Okay. For example, some common hyperparameters are learning rate, number of hidden layers, number of neurons, batch size, reports, activation functions, optimizer, dropout rate. These things we can customize the values of these hyperparameters according to our need. That is what hyperparameter tuning. Okay. So in this video, we will see early stopping and regularization technique. Okay. On same model we have created. So in our previous video, I have built a model using ANN. So our accuracy was something around 85%. Okay, 85.5%. So I did some customization on the same model. Okay, what I did, I gave I gave random state as 10 instead of 42. Okay, so you can see now my model is little bit overfitted. Okay, now let's see if I will use early stopping or regularization techniques, my model gets improved, will improve or not. Okay, so let's see how we can do it. First, I will run all these cells. Yeah, here I need to add from Keras dot regularization. I just import. Suppose I will import L2. Okay, and second thing from Keras dot callbacks. import from Keras.callbacks import early stopping. Early stopping. I have imported two things, L2 regularizer and early stopping. Okay. So, so in the first layer, Keras values import L2. That was some styling mistakes. Okay. Now it gets imported. Now, now what I will do, I need to add some hyperparameter. I need to add, you can see kernel constant bias. Yeah, I need to add this one. Kernel regularizer. Okay. Here its default value is given none. But I will add now L2. L2 regularizer I am using. Okay. What I will do? I will do L2 parenthesis shift plus tab. Now default value you can see L2 is equal to 0, 0.01 you can see. So I will take the exact value. Okay. Now let's see my model will be improved or not. I will run all the cells. No, no, my model accuracy is not improved. Now let's check by early stopping too. Okay, so here I need to add, here I need to add callbacks. You can see here its default value is given callback, none, sorry. Its default value is given none, but I will customize this to early stopping. I will add early stopping, early stopping. Okay, what early stopping will do? It will stop training the model when it will realize that your model is will get overfitted now. It will then stop training the model. Now, let's run this. Yeah, you can see here on second approach, it has not trained completely, right? And let's see. Now, it gets stopped on second approach. Now, let's see my model is improved or not. No, still not. Now let's check again by giving random state is equal to 42. 42. So yeah, again I got the accuracy of 85% and overfitting is gone. Okay, so maybe some other factors will uh, improve this model. So, but that's how we can apply early stopping and L1 or L2 regularization. Okay, here you can import L1 also or L1 and L2 both together also. So you can apply these things like this. Okay, for L2 regularization, you need to include this in your first hidden layer which you are creating. So these three hidden layers I have created, and this was my first hidden layer. And here, when I was fitting the training data into our model, then we need to use early stopping, okay, as callbacks hyperparameter, okay. So that is how early stopping and regularization we can apply to our model, okay. So that's all in this video. In the next video, we will discuss batch normalization, okay, and then we will see hyperparameter tuning also, okay. So thank you. Hello guys, welcome to the channel. So our today's topic is batch normalization. So what is batch normalization? Batch normalization is a technique that normalizes the output of a layer for every mini batch during training so that the neural network learns faster and more steps. In other words, it keeps the data distribution similar throughout training. Okay, now let's understand this. So without batch talk, suppose one neuron receives value like 5, 12, 25, 80, 150, like this. But another time when it receives 0.2, 0.4, 0.7, 1.1. So this is how value we are receiving. It is receiving, okay, neuron. So the neuron has to keep adjusting itself, okay, because the values are changing repeatedly, okay. So then learning becomes difficult. So by using batch normalization, we scale the value, like it convert the value something like this: minus 1.2, minus 0.5, 0.1, 0.8, 1.4. Now every layer gets inputs in a similar range. So that's how training becomes much easier. You can understand this, okay, by, let's say, when we built ANN, customer churn prediction model using ANN, so we scale the input features, right, by standardization, like this, right. If you can see here, you can see these values of input features, and here you can see after standardization these values scaled to these values. Okay, so this is all. But these are for input values. We did it by standardization for input features. But what about hidden layer? But what about inputs in hidden layer? Let me show you. Here is my hidden layer. Yeah, we standardize the inputs here. We standardize it. But what about the inputs in hidden layers? How to normalize, how to basically scale the values. in hidden layer. For that case, we use batch normalization. Okay. For that case, we use batch normalization. We use batch normalization for each hidden layer. Okay. So let's see how we can do it. Again, I'm taking the uh, previous customer churn prediction model. Okay, so again I have done some customization to make it overfitted. Like I did random state is equal to 10 instead of 42, and I changed epochs to 10 from 50. Okay, now how to perform batch normalization for all hidden layers. Okay, so so these three are my hidden layers, and this last one is my output layer. Okay, I've already discussed this when I was making this model. Okay, so these are my hidden layers. So how to add batch normalization to scale the value, okay, for each hidden layer? So for that I need to add batch normalization here from keras.layers with dense. You need to add batch normalization, batch normalization. Okay, now shift plus enter, again shift plus enter. So now now we need to add batch normalization for each layer to scale the values. Okay, so how we can do it? So I will just write ann dot add batch batch normalization. Okay, now I will simply copy this and paste this to my each layer. And remember that don't add your batch normalization to your output layer. Only add to the hidden layers. Okay. Now let's see. I click shift plus enter, shift plus enter. Now let's see. Model is getting trained. So yeah, before I was getting 78% accuracy and 79% accuracy for the, sorry, 78% accuracy for the testing and 79% for the training. Okay, now we are getting 83.95% accuracy. Okay, 83.95 accuracy for testing and 84.5 for training. Still you can see there is a overfitting, because you can see accuracy of training for training data is higher than this testing data, right? So this means it is a case of overfitting, but it quite reduced, it is like reduced the overfitting, right? From like 0.55% it is getting overfitted. So yeah, it reduced the overfitting, and also it improved my accuracy, right? By adding batch normalization to each layer to basically to scale the values, right? So my model accuracy gets improved, and it is quietly basically reduced overfitting also. So this is how batch normalization we can perform to my model. We need to just import batch normalization from layers, keras.layers, and then we need to add batch normalization to each layer, to each hidden layer, not output layer. Okay, so this is how batch normalization works. Okay, so in the next video we will see dropout layer. Okay, so that's all in this video. Thank you. Hello guys, welcome to the channel. So our today's video is dropout layer. So what is dropout layer? A dropout layer is a regularization technique used in deep learning to reduce overfitting. Okay. So what we do in dropout layer, how we perform dropout layer. During training, it randomly turns some neurons off, means it drops some neurons. So the model does not become too dependent on few neurons. Okay. So what does randomly drop mean? Means it will randomly drop some neurons. So every training iteration, the model randomly selects neurons to remove. Okay, for example, iteration one, you can see this crossbar. This is dropped neuron. Okay, in iteration one, these two neurons were dropped. In iteration one, these neurons were dropped. Iteration two, these two neurons were dropped. Iteration three, these neurons were dropped. Okay, so this is how drop neurons keeps changing. Okay, so there is one important term, dropout rate. So the dropout rate tells us what percentage of neurons should be removed. For example, dropout is equal to 0.2. Then 20% of neurons from that particular iteration will be dropped, and active and 80% will remain active. Okay, so during training, dropout is active, means we will perform dropout during training. Some neurons are randomly turned off. Every batch uses a slightly different network. Okay. So because of this, the model becomes more robust and learns better features. Okay. And during testing, here during testing, no neurons will be dropped. Means dropout layer will be not active for testing. Okay. So the complete network will be used. So because why we will not drop the neurons here? Because we want the model to use all the knowledge it has learned. Okay, so during training, dropout will be on, and during testing, dropout will be off. Okay, so let's see how we can add dropout layer to my during my training. Okay, so again, I will use customer churn prediction model for this. Okay, so I have done some customization to make it overfitted. So here you can see its accuracy 81 point for training, 79% for testing. So this is clearly showing this is overfitted. Okay, let's rerun this. Yeah, yeah. Here, here you need to add from Keras.layers import dense. With dense you need to import dropout dropout layer. Sorry, dropout, only dropout. This is dropout. I have imported from Keras.layers. Okay. Now in our previous video we saw we added batch normalization to each hidden layer. This last one is your output layer, and these three are your hidden layers. So we added batch normalization to each layer. So exactly in the same way, this time I will add dropout. So I will simply I will write ann dot add. I will call my dropout, and and here you can see what we need to give the dropout rate. Okay. Suppose I am giving dropout rate as 0.2 to each layer. I will simply copy this. I will paste this to all my hidden layers. Okay. So you can customize this also. You here in the first layer you have added 0.2. Here you can add 0.3, 0.1, anything. You can customize that. Okay. Uh, to reduce overfitting. Okay. So don't add dropout to your output layer. This last one is your output layer. Don't add dropout layer to this. Okay, now let me run this and let me check if it removed my if it will remove my overfitting or not. Okay, so it is getting drained. Okay, and then yeah, it basically decreased my accuracy also, but little bit it reduced my overfitting. Okay, here you can see 78.9 and 79.81. There was difference of 2. Now it has a difference of something around 0.9. So it reduced a little bit overfitting, but it also decreased my accuracy. So let me customize this more. Let me add 0.3. Okay, and let me rerun this. Uh, Maybe accuracy decreased because I think I have decreased the quotes also. 10, we can add 50, 30 quotes to increase my accuracy. Okay, so let's check this. No, it's still it is overfitted. Okay, so like 0.9 is 0.9 is the difference between these two accuracies. So it is little bit overfitted, but this is how dropout layer reduces overfitting. Okay, so you can keep customize this value 0.2, 0.3, 0.2 like this. Okay, so until and unless you uh, basically overfitting should be removed. So this is how we add dropout layer to all hidden layers, not output layer. Remember that, not output layer, only hidden layers. From we will first import dropout from keras.layer with dense, and then we will add dropout to each hidden layer, not output layer. Okay, so this is how dropout layer works. Okay, to reduce overfitting. So that's all in this video. In the next video, we will discuss hyperparameter tuning. Okay, thank you. Hello guys, welcome to the channel. So our today's video is hyperparameter tuning. So before understanding hyperparameter tuning, first understand what is gradient descent problem. So gradient descent helps us minimize the loss function, but during training, it doesn't always work perfectly. Understand this. Gradient descent is a technique to minimize the loss function, but during training, it doesn't always work perfectly, right? So sometimes the model learns slowly, sometimes it gets stuck, sometimes it keeps jumping around. So these are called some gradient descent problems. Okay, so let's see problem number one as an example. Learning rate too small. Suppose learning rate I have given this 0.0000001. So the model takes extremely teeny steps. Okay, imagine climbing down a mountain. Instead of taking normal steps, you move only 1 millimeter each time. So that is how learning rate too small works. Okay, so it will take forever to reach the bottom. So similarly, the neural network learns very slowly. Okay, so problem number two. Suppose learning rate too large, then suppose I have given learning rate is equal to 10. So now imagine taking giant jumps while climbing down a mountain. Okay. So instead of reaching the bottom, you keep jumping from one side to another. Okay. You will never stop. So similarly, the model overshoots the minimum loss. Okay. So this is the problem of gradient descent. Okay. So now let's understand hyperparameter tuning. Hyperparameter tuning, I have already discussed during my machine learning lecture also. So understand this here also for deep learning. Hyperparameter tuning is the process of finding the best combination of hyperparameter to achieve the best model performance. Instead of guessing values, we try different combinations and choose the one that gives the lowest validation loss or the highest validation accuracy. Okay, So these are some common hyperparameters. I have already discussed learning rate, number of hidden layers, number of neurons, batch size, epochs, activation functions, optimizers, dropout rate. So these are some your hyperparameters. Okay. So you just need to customize these values according to your data, according to your model to get the higher accuracy. Okay. So let's see how we can do it. I'm again taking customer churn prediction model. So let's understand this, how we can do. I will rerun this. Now, first thing is your, let's say, number of hidden layers. You can increase your hidden layers. Okay. You can just copy this. These three are your hidden layers, and this last one is your output layer. So you can increase your hidden layers. Okay. You can increase your hidden layers. Suppose now I have one, two, three, four, five. So we can just, so this is also a kind of hyperparameter tuning. I have added more hidden layers, and I am basically changing the number of neurons here. 6, 5, 4, 3, let's say 3. Okay. So I'm changing the number of neurons also, and I have added some hidden layers, more hidden layers. Two more hidden layers I have added. So this is a kind of hyperparameter tuning. Okay. So let's run this now. Now we can customize as optimizer. If you will see here, Shift plus Tab, you can see your default optimizer is RMS prop. You can use this one also, or uh, you have SDD and many types of optimizer you can use, but generally we use Adam. Okay, so if you have regression problem, there is a different loss function for that. Okay, so this also like we can customize optimizer loss. Okay, so this is also a kind of hyperparameter tuning, but this is a binary classification problem. So we will use binary cross entropy. Okay, so here you can see shift plus tab. Now look at these hyperparameters. You can customize these hyperparameters. Okay. Now see here you have batch size. Batch size you can take. You can customize her like 60. Epochs you can take suppose 30. These things you can customize. Okay, you can check your model on different values of hyperparameters and choose the best hyperparameter values for your model. Okay, so you can customize these things also. Okay, you can add learning rate also. So this is how hyperparameter tuning works. You just need to basically customize the values of your hyperparameters according to your need. Okay, this is what hyperparameter tuning is. Okay, so that's all in this video. This is how we can perform hyperparameter tuning. And in the next video, we will discuss CNN. Okay, so that's all in this video. Thank you. Hello guys, welcome to the channel. So our today's video is convolutional neural network. Okay, so what is convolutional neural network, CNN? So it is a type of deep learning model specially designed to work with images. Okay. So it automatically learns important features from images like edges, shapes, patterns, objects. Okay. These things it basically automatically learns from the images. Okay. So we don't need to give features like we need to give some inputs to that. Only we need to give images as an input, not like too many features. Okay, it will automatically understand the image and it will learn these patterns. Okay, learn these things from images automatically. So, like we have given some features in machine learning algorithms ANN, then it predicted the output, right? But in this case, we just need to give the images, okay, to to get the prediction. Okay, so in simple definition, you can say CNN is a deep learning algorithm that automatically extracts most basically. important features from images and uses them to classify or recognize objects. Okay, this is a simple definition. Okay, so why do we need CNN? Imagine you want a computer to identify whether an image contains a dog or a cat. Okay, so what if I will use ANN instead of CNN? Then we will need to give, it will takes every pixel as an input. We will need to give this as a feature. Images have thousands or millions of pixels, so we will have too many parameters. We will need to give too many features. Okay, so model become very slow. Okay, and it will be easily overfitted. Okay, so that is the problem with KNN, working with large amount of data sets like images. Okay, which have like millions of pixels. Okay, so CNN solves this problem by automatically extracting only the important information from the image. Okay, so these are some real life examples like face recognition of CNN, basically face recognition, self-driving cars, medical image analysis, object detection, OCR, reading text from images, security cameras, handwriting recognition, fingerprint detection. Okay, so here you can see the complete flow of CNN. Okay, here you are given the input. Then every time you will zoom an image. Anytime you will zoom an image, you will see some small boxes in your image. Okay, so that is your kernel. Okay, so here you can see pooling, convolution, ReLU, flattened layer, then fully connected layer, then output. These are the complete slew of convolutional neural network. So input image, convolution, ReLU, then again, then pooling, then again it will repeat convolution, ReLU, pooling. Then after repetition of these steps, then it will flatten, then fully connected layer, output prediction. So this is the flow of CNN. So let's understand each and every step in detail. Okay. So step one is your input image. So this is the image that we give to the CNN, right? Example, a cat image. Suppose the image size is the dimension of the image is 128 into 128 into 3. What it means? 128 is your height, 128 is your width, and 3 is your RGB, red, green, blue. This is your color. Every pixel has a value between 0 and 255. Okay. So the CNN cannot understand cat. It will only understand the numbers. It will only see the numbers. Okay. So now step two. So convolution layer is the most important layer in the CN. Okay. So here what CNN do here? What CNN does here? CNN tries to find useful patterns in the image in convolutional layer step. Okay. So it does this using a filter called kernel. Kernel. This is your filter. This is your kernel. Okay. So what it will do, it basically find useful patterns in the image using filter kernel. So for example, you have this filter 101, 010, 101. This is your filter. Okay. So the filter moves over the image from the left to right and top to bottom. Imagine placing a small window on the image. Suppose this is your image and this blue part is your filter. 101, 010, and 001. This is your filter. So what it will do, it will basically checks on only this small part of the image here. Here. Then it will repeat this. It will check on this. It will check on this part. It will check on this part. It will get repeated. This step will be repeated again and again. Okay. So now here it shifted this. Now it is learning this pattern. This area of image. Okay, so what happened inside the filter? Suppose the image patch is 1, 2, 3, 4, 5, 6, 7, 8, 9, and we applied a filter 101, 010, and 101. So now it will multiply corresponding values 1 to 1 to 1 into 0, 2 into 0. Now this is how it will multiply from this one. Okay, 101, 010, and 101. Now at the last it will add this value. Okay, after multiplying each patch. Okay, suppose I got 25, so one output pixel becomes 25. Okay, then the filter moves to the next location and repeats the process. Remember this is only for this one part only. It will be repeated to the next part. It will be repeated to the next part. Okay, so let me show you how it basically learns from an image. Okay, now let's see. I have this website. Okay, so this is the image. This is the input image. Now let's see how it learns. If I will play it now, let's see. Here you can see. This is learning. This is learning. Okay, see, this is how filter works. This is your filter. This is your filter. How filter works. Okay, it checks every part of the image. It will check every part of the image. Okay, so see, this is how it works. Yeah, can you see this pattern? I will move my cursor over here, and it will move on this part also. Here you can see. Can you relate this? Will you able to relate this? Yeah. This is how it works. This is how convolutional layer works. Okay. See, I will move this cursor over here. It will move it at the same place on the left side image. Okay. This is how it works. Okay. So this is how convolutional layer works. This example for only one part. It will repeat. It will be repeated on all the parts. Okay. Now, third step is your ReLU layer. So after convolutional layer, some values are positive and some values are negative. Okay. So for example, I got these values -5, 10, -3, 8, 2, -7. I got these values. So, ReLU's mathematical expression is this max 0 by 0 comma x. So what it does? So if the value is negative, then make it 0. If the value is positive, then keep it as it is. Okay. So for example, I had these values -5, 10, -3, 8, 2, -7. Okay. So after ReLU applied, it will become 0, -5 to 0. 10 will be as it is because it is positive number. -3 will be 0, and -7 will become 0. So this is what ReLU does. Okay, okay. Now fourth step is your pooling layer. So after convolution and ReLU step, the feature map is still large, right? You can see 0, 10, 0, 8, 2, like this. So pooling reduces its size. Suppose we have this feature map 251487623195 like this. So let's see max pooling. Take it 2 into 2 window 2587. Okay, 2587. Now it will choose the highest number. It is 8. Then it will move to the next window. Next window. Suppose 1462. 1462. After 2587, it will move to the 1462. After this part, it will move to 1462. Okay. Now it will choose the maximum, that is 6. Then it will move to the next part. What is your next part? 3142. This one 3142. Now it will choose the highest number, then that is 4. Then the last one 9587. It will choose the highest number 9. So now it will become 8649 after combining all highest numbers from each window. it became 8649. So you can see the size became much smaller. Okay. So this is how pooling layer works. Okay. So uh, what are the uses of pooling? It reduces image size, makes training faster, reduces memory uses, and helps prevent overfitting. This is the most important thing. Helps prevent overfitting. Keeps the strongest features. Okay. So after these steps, it will repeat again and again. It will repeat again and again till pooling. Till pooling, it will repeat again and again this process. Why we repeat this process? Because only one round of these steps is usually not enough to understand a complex image. Okay. So we need to basically repeat these processes, convolution to ReLU and ReLU to pooling. We need to repeat these steps again and again. Okay, because one round will be not enough to understand a complex image. Okay, so we need to repeat this process again and again. Okay, so after this step, after repeating these steps, and now our step 5, flattened layer comes into play. Okay, so after several rounds of convolution and cooling, the output is still a 3D structure. Okay, so a fully connected layer, here you can see in the image, this is fully connected layer can't process a 3D data. Okay, it will not process 3D data. So that's why we need flattened layer. Okay, that's why we need flattened layer. Okay, so we flattened that 3D data into a single list, 1D vector. Because before it was 7 into 7 into 64, we applied flatten, it becomes 3136 values. Okay, multiply this. Okay, like this 5821 271, like this to 3136 number. Okay, so this is how it converted a 3D data into 1D vector. Okay, now here's your next step, fully connected layer. So this layer works exactly like an ANN, where we use hidden layers, okay, and then output layer. So this works as like an ANN, okay. So every neuron is connected to every neuron in the next layer, okay. So it takes all the extracted features and tries to answer basically which object is this. For example, we if we are classifying cat and dog, it will basically, it might have learned two eyes, two ear, whiskers, tail. So these things it may learn. Okay. So now the fully connected layer combines all these features to decide that the image is most likely a cat or dog, whatever it has learned. So now last step is your output layer, where we give prediction. If I have binary classification, suppose I have 0.98 for the cat. So highest probability is your cat. So it will predict cat. Okay. If you have multi-class classification problem, then suppose it has given a prediction of like 90% for the chances of cat, 5% for the dog, 3% for the cow, 2% for the horse. Then it will predict again cat because it has the higher chances. Okay. So that is how CNN works. I have explained all these 7 steps. Okay. You can see here. I have explained all the steps one by one, complete flow of CNN. And I have also explained how it works, how it learns from an image, like how a filter is applied to learn from an image. This is how it works. Okay. This is how it works. This is how it learns from an image. It will cover all part of image. We can decrease the size of this output image as well. Okay, so you can see here this pattern it has developed using this. Okay, so this is how CNN works. So that is all about CNN overview. In the next part, we will do a project using CNN. We will do an interesting project using CNN. Okay, so that's all in this video. Thank you. Hello guys, welcome to the channel. So in this video, we are going to do a project that is bone fracture detection using CNN. Okay, so I have two folders here. One is for training dataset, and under this I have two folders, fractured and non-fractured. In fractured folder, I have around 4,475 images of fractured bone. Okay, and in non-fractured folder, I have around 4,379 images of non-fractured bones. Okay. Similarly, I have a testing data set in which I have around 360 images of fractured bones, and in non-fractured folder, I have around 240 images of non-fractured bones. Okay. So let's see how we can build a model using CNN to predict by an image that the bone is fractured or not. Okay, so let's see how we can do it. First, I will import TensorFlow. Okay, so sometimes it take some time. Okay, till then I will write the syntax for importing something, some few things. So I need to import Keras dot models. I need to import sequential. Okay, and from Keras dot layers, I need to import few things like conv 2D. Okay, and for making convolution layer, I need to import con 2D, and for pooling step, I need to import max pooling 2D. I need to import flatten. Then I need to import dense. Okay, it will be capital C. And then I need to import dropout also. Okay. And last thing, I will import from Keras dot pre-processing dot image import image image data image data generator. Okay. Now need to add here TensorFlow dot Keras. Okay. Now all the things I have imported. Now let's make an object to call my sequential. Now now I need to make some convolution block. That is this. Okay. So I have input. I will like give input when I will fit the model. Then first I will do this part. I will make some convolution block. Okay. So let's see how we can do it. This step. I've already explained these steps one by one. Okay. In my previous video, and you can check my previous video where I have given overview of all the steps we need to perform. This is the workflow of CNN. I've already explained. So first thing, I will make some convolution layer. Okay. And now let's see how we can do it. So let's say I will create first convolution layer. I will my I will call my con 2D con 2D. Then I will pass some hyperparameters. If I will click Shift plus Tab, I will give some filter, some kernel size. Okay, activation. I will give ReLU. Okay, ReLU activation. I will give some input shape also. Okay, so these hyperparameters I will give here. Now, first thing I will give filters. Let's say I will give 32. Okay, and then these hyperparameters I've already explained in my previous video. We can check my previous video where I've given overview of all the things. I will give kernel size as suppose I will give 3 comma 3. I will give some activation. I will give ReLU and input shape. I will give as I will give some dimension like 128 height and 128 width and 3 for its color RGB. Okay, and then I will add pooling in here. You can see I have already explained the next step. I have given our ReLU layer and then I need to add pooling layer also. Okay, so that it can reduce its size. Okay, so for the first block I will add some pooling. For that I will give max pooling 2D. Now I will here pool size as given 2 by 2 comma 2. I will use this rest parameters. I will not use hyperparameter. Sorry, I will give pool size as 2 comma 2. Okay. Now this is my first convolution block. I will suppose add two more convolution block. Okay, I will simply copy this. I will again copy this. Okay. Now I will take suppose 64 here as filters and rest all the things input. Input shape you don't need to give again. Okay, so again you don't need to give this here. One more parenthesis. Yeah, I will give this filters as suppose 128. Okay, rest all the things I will keep same. Okay, so 2 by 2. Next putting will be 2 by 2, and then I will run this. Okay, so I have created some, I have given some convolution block here. So my second step is the convolution layer, and also with that I have added ReLU layer and pooling layer also. Now, 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 uh, now the next part, uh, next step is giving flatten layer because I have already explained what flatten layer do. Here you can see I have already explained on step 5. Basically, it converts 3D data into 1D vector. Okay, so I will add here, I will add here only CNN dot add. I will give flatten. Okay, so yeah, so I have given flatten. Now, next thing we will do, we will create fully connected layer like ANN. Okay, I will make some hidden layers. Okay, like I did when I was creating a model using ANN. Okay, same steps I will do here. Now, CNN dot add. I will call dense. I will give suppose number of neurons as 256, comma, and I will give activation as ReLU. Okay, and I will give some dropout also. I've already explained dropout in my previous videos. So you can check. Basically, dropout is used for reducing overfitting. So I will add some dropout here. Dropout. I will give some dropout as suppose 0.5. I need to remove 0.5 means 50% neurons. Okay. And then suppose I will create another hidden layer. CNN dot. I will simply copy this. Now I will give suppose 128. Okay. And then lastly I need to create a output layer. Okay, this one, this is my output layer, and these are my hidden layer. I've created two hidden layers and one output layer I will create. Few terms if you are not getting, I have already explained each and every term in my previous video. I will upload one more video of complete deep learning course. You can check that. You can complete that video also from starting to end. You will understand each and every term. Okay. So I will create an output layer, dense, and I will give suppose as one neurons because I will have only one output at a single time. Activation. This time I will use activation as sigmoid because this is the problem of binary classification. And sigmoid's range is 0 to 1. Okay, so I have created hidden layers and one output layer also, and I have added dropout also to a hidden layer. Okay, now I will compile the model. CNN dot compile. You will click here, press tab. Optimizer, default optimizer is your RMS prop, but I will not use this. I will use Adam as my optimizer, Adam. And second thing, I will give loss. Loss here it is default is none, but I will give binary cross entropy because it is a problem of binary classification. Binary cross entropy, and lastly, I will give matrix accuracy. Okay. Now, now I need to fit the model. Okay. So you don't need to remember the code of CNN dot fit. You can simply go to the documentation of Keras Python documentation, and here you will go and search something like image generator. Okay, and then go to this one because I need to do image classification using small data set. So here, if you will scroll down, yeah, this is your code of CNN.fit. Okay, this is how you are going to fit your model. You can simply copy the code here. You will paste it here. Okay, same thing, paste here. Now this one I don't need here, and we will do some customization here. Batch size I will comment. I will give manually here. Okay. And then I will give some train data generator range. I will give suppose I will give rotation range here instead of shear range. I will give some rotation range as 20. Okay. So now test gen is perfectly fine. Train gen I will give here my path. I will give R so that it can read. This is my train folder. So I will right click, copy path. Give the I will give the path here. Okay. This is the path. Okay. And target size, I will give, I will do some customization. I need 128 into 128 because I have taken dimension as 128 into 128 here. So I will give 128 and 128. Okay. And batch size, as I have commented, batch size, I will give 32. Okay. Suppose I will give 32 and then for test, this is validation generator. I will rename this. I will rename this to test generator, test generator, and then I will give path again to my test for my test data. I will give read and then simply this will be also test. Okay, test, and again I have taken 128 into 128 dimension. So I will give 128 into 128 height and width. Okay, batch size again I will give 32. Okay, and then I will give one more hyperparameter here. I will give here shuffle is equal to false. Shuffle is equal to false. Okay, and now here uh, it also because I have renamed the file, so you need to give test generator, not validation generator. And here you don't need to write slash generator. Suppose I will store this in a variable. This is equal to suppose CNN dot fit. I will use this one. Okay, and sorry, fit. Yeah. So I will give here train generator equals. I will give suppose 15. That is a large number of 50 was a large number of echoes. So I will give this. I don't need to give steps per echoes because we don't need to write steps per echoes. Keras will calculate it automatically. So I will comment this, and next thing I will comment validation steps also. We don't need this. Okay. So I will simply comment this also. Last one, and I will run this. Okay, so it is getting trained now. Now, so finally my model got trained because I have used all the images I had, uh, around 9,000 9,000 images something. So it took around 45 minutes to get trained. Now my model is finally got trained. Now I will make some prediction using my some unseen images, or you can say unseen data. Now I will import from Keras dot pre-processing, import image, and I will import NumPy as well as entry. Okay. Now I will make a variable image img. I will call image dot load slash img. Now I will give the path. of my image. So there are four images of four fracture bone, and there are four images for not fracture bone. I will give this for the first one. Will right click, copy path. I will paste it here, and I will give target size. Target size is equal to 128, 128 height and width, because I have taken 128 by 128 previously also. So I have given the target size. Now I will convert this image to array. I will convert image.img slash 2 dot slash array. I will give img this image. I will give, and I will give this. I will divide by 255.0. Okay. Now, now img is equal to, I will see, expand dimension, and p dot expand things means dimension. I will give my image, and I will give axis is equal to 0. Okay, and I will give prediction. I will make a variable prediction, and in the variable prediction I will give CNN dot predict my image. Okay, and I will print my prediction. Okay, I need to give a 3 as well. Okay, now you can see I'm getting 0.01 for the fracture 1 image. Okay, so it means I will get, you can how you can basically divide your fracture and non-fracture between 0 and 1. There will be a classification between 0 to 5, and another will be 0 0.5 to 1, right? So it means my fractured bone will lie around 0 to 0.5, and my non-fractured bone will lie 0.5 to 1. Okay, so I will write a condition here. If prediction 0, 0 greater than 0.5, then greater than 0.0, greater than 0.5, then print no fracture, no fracture. Okay, and because we are getting 0.0 means we will get 0 to 0 to 0.5 for our fractured bone, and 0.5 to 1 for not fractured, non-fractured bone. Okay, or I will say else print bone fractured. Okay, so here I got bone fractured. Now let's check by replacing another fractured bone. Sorry, fractured 2. Right click, copy path. I will paste it here. Let's see. Yeah, for second fracture bone, I also got bone fractured. For the third one, let's see, copy path, and let's see what what I will get. Yeah, for third fractured bone image, I got bone fractured as my output. Now let's check on not fracture. Copy path. I will paste it here. Yeah, you can see here. For not fractured bone, we got no fracture, right? For not fracture bone, we got the output no fracture. And here you can see the value 0.65 that was greater than 0.5. So what I described earlier, when I will have some non-fracture bone, then the value will lie into 0.5 to 1, and for the fracture bone, the value will lie 0.0 to 0.5. Okay, so here I got no fracture. Now let's check for the second not fracture bone image. Copy path. I will paste it here. Okay, let's check. Let's check. Okay, so I got a wrong output here on fracture non not fractured 2 second image. First image I got the correct value for all three images of fractured image. I got the right value. For the second not fracture I got the wrong value. Let's check on third image of not fracture. Let's check. So yeah. So again, on the third image, I got the right value, no fracture. But remember, for second picture, I got the wrong value here as bone fracture. Let's check on the last one, fourth image. Let's check. So yeah, again, no fracture. I got the correct value. So yeah, uh, on on one image, I got the wrong answer. Remaining all the input image I am giving, I am getting the correct out. Let's check on the last image of fractured bone. What it will give prediction here. And yeah, it gets corrected right. So I got all the correct answers for fractured bones, and I got correct answers for three images here. And but I got one wrong answer for not fracture bone. Okay, so that's all in this video. We have built a model, and it is a quite good model. It is giving correct answers on almost all inputs. It is giving correct answers to me. So it is quite good model we have built today. So that's all in this video. Thank thank you.